Good morning, everyone. Welcome to our deep dive into the heart of modern network security. So, today we are moving beyond theory to look at the math that underpins trust on the internet. So, our focus is the secure hash algorithm, which is the SHA 256, and its most vital feature is the avalanche effect. So, this isn't just theory, it's the engine that powers everything from the secure passwords to global cryptocurrency. So, what is a cryptographic hash function? So, we say it is a mathematical algorithm that transforms data of any size into a fixed length string of bits. So, in simple terms, it is just a mathematical blender. You take any piece of data, which is a single word or a terabyte of or a video file, so that is considered as your input. And when you put your input into a hash function and it outcomes a fixed size or a string of characters, so that is the output and that is called the hash value. So for example, like for SHA 256, the output is always 256 bits long. So which we represent a 64 character hexadecimal string. So crucially, this process is always one way. So it is very easy to hash the data, but computationally it is impossible to reverse it and find the original input. So this one way street is the foundation of security. Next, we say the need for hashing. So, we say there are different use cases. So, why do we need this one way blender, or why should we just make data more complex so that it is difficult? So, we need, we need because there are three reasons. First one is password storage. So, a secure system never stores your actual password, it just stores the hash of your password. So when you log in, your input is hashed. So and the two hashes are compared. The password itself is never exposed. Second is the file integrity. So if you download a critical software update, so how do you know a hacker hasn't slipped a malicious code into it? So you just calculate the file's hash and compare it to the original hash. So published by the company. So if the both hashes match, we consider that as it is authentic. And finally, it is digital signatures and blockchain. So, digital signatures are used extensively in transactions and blockchain technology to verify that a document has not been altered since it was signed. It is very useful. Going on, introducing the SHA 256, which is the industry standard. So, we say that it is the gold standard because it is developed by the NSA and used globally. So its output size is fixed, which is 256 bits. So to be considered, which is like truly secure, a hash function must satisfy three properties: determinism, pre-image resistance, and collision. Going on, the property one is determinism, which is the repeatable fingerprint. So it is just so straightforward. Determinism is straightforward. Like if I hash the input network security once, I get this 64 character hex string. So if I hash the exact same input a million times, I get the same exact output exactly. So even though if I'm computing the same word, I get the same hash function. But once when I include an exclamatory mark, like I can see you using a pointer, the hash function is completely changed, right? So exactly. So that is the exact mechanism working over here. And the property 2 is pre-image resistance, which is one-way security. So pre-image resistance is where the massive numbers come in. So like think of the analogy. I've just put an egg over here, which is scrambling an egg. So it is easy to scramble it, but it is impossible to unscramble it. So the hash output space is vast. So you can see the output space is 2 power 256. So there are these much possible combinations where you can brute force or guessing the input is just very hard and it is just impossible. Going on, property 3, collision resistance. So this is the property that stops the attackers dead in their tracks. So collision resistance means it's incredible to it's really hard to find two different input messages that produce the exact same hash in output. So, if collisions were easy to find, an attacker could take a legal contract, which means they can create a version of this contract and then engineer it to produce the same hash. So, the system would verify the signature, thinking it was the original document. So, this is why it is so critical. So, how does this SHA 256 produce or no guarantee this resistance is using the avalanche effect. Going on, avalanche effect. So, or what is our goal? It is just to introduce or to attain 50% of the ideal target. So, avalanche effect is just the core cryptographic mechanism. It dictates that even the slightest change to the input, just like we saw, no, just including an exclamatory mark. So even if you flip one bit also, this will trigger a massive a cascading change across the entire output. So for our 256-bit hash, so the ideal outcome is that roughly it could be 128 bits or 50% of the hash. So output should flip randomly. So we want chaos, but we want chaos, but we don't want total unpredictability. So imagine that a small trigger, like example a snowflake, which is creating a total avalanche in the resulting hash. So I've just included a picture for you to understand what is avalanche, because even when you like introduce a small change, that will result in an entire unrecognizability. Next comes the avalanche effect, which is quantifying the chaos. So here we can see an example, which is the first sentence, which is the key is 8, where the E is very small, which is the original input. But when you change the small e to the capital E, you can say you can like once when you see the change in the input directly, it is very you can think it is very minimal. But when you see the hash which is completely changed, no, so it is totally there is no correlation between these two. So this is avalanche effect. So basically our goal is to quantify how many bits flip in the final 256 output. Going on, so now we are going to see a real world application, which is the Bitcoin key derivation. So we are just going to transform a secret number into a public address. The first step is the secret key, which is the private key, which is small d. So everything begins with the step 1, the secret or private key. So this is the most crucial part of the entire system, because numerically we can say that it is just a random 256-bit integer, but that is a number with 77 digits, and we typically represent it as a 64 character hexadecimal, also called as 32 bytes. So, going on, the security is based entirely on the randomness of this number. So, if it is ever compromised, if the if it is considered to be simple, all funds secured by it are compromised. So, the security is also compromised. So, this is why this table emphasizes. So, it should remain secret. Going on to the step 2, which is the core operation, which is where the component is scalar multiplication. So the bits from secret to public is step 2. So here the elliptic curve math is applied. So we take a private key small d and we multiply it by a public, or we can say it is a base point g. So the result is going to be the public key, which is q. Yeah, so everyone know what is ECC math function. It is a one-way function. So we can calculate q, which is the public key. So now we have our own public key. So from this we also have our private key. So next we are going to the step 3, which is the public key. So the result of this is this multiplication, this scalar multiplication is that it is going to generate a public key. Yeah, we already saw. So this key is a geometric point which is x comma y. So this x comma y is a point on the elliptic curve. Since the coordinates are two separate 256-bit integers, the key effectively doubles in the size to 512 bits. So unlike the private key, the public key is shared freely. So only a private key is meant to be kept secret, but this public key can be shared freely for receiving the funds. So thinking of it like your bank account number. So your account number, you can share it to everyone, it's public, but sharing your secret pin is very stupid way, because nobody would do that, right? Next comes step 4, address derivation. So now we have x comma y, which is a 512-bit key, which is still too long and complex for people to use easily. So we just shorten it using the step called address derivation. So the main component you use here is hashing chain. So we apply a chain of cryptographic hash functions, which is SHA-256 followed by RIPEMD, which is a 160 to the public key, because the first hash which scrambles it, and the second hash dramatically reduces its sign to the 160 bits. So finally a base 58 check is used to encode any errors, and it converts this binary data into a compact and an alphanumeric string, right? So this reduces the 512 public key down to a short usable string of 25 to 35 characters. So here you can see final numerical output. So this is going to be a Bitcoin address, and what is going to be the key principle we are going to remember is that the security is derived entirely from the infeasibility of reversing. So reversing a public key and address that everyone can see. So while keeping the secret private key which is kept mathematically hidden forever. Going on to the end of this video lecture, so we are going to summarize that what we have learned, which is hashing is a one-way function. So the math we are doing, it is making that impossible to reverse. And one more thing, 125 bits are flipped, which is collision resistance, which is critical to prevent fraud or data trampling, right? And the avalanche effect. So this avalanche effect is the engine, or it is a measurable numerical chaos demonstrated, so that there are 48.8%, there is a percentage in the bit flip, which makes the SHA-256 secure cryptographic primitive. And also you can see the collision infeasibility is to the power of 2 power 256, which is a very massive search space, and it is impossible for you to guess what is the original input. And so the ultimate security principle here is that even a tiniest change to a message is instantly detected by the resulting massive change to the hash. So thank you, and I hope you understood this lecture.